into the next episode. So in this episode, we will go into linear algebra like always, but this time around we'll be talking about subspace. So today we are doing subspace. So let's dive in. Now, what is a subspace? Now, a subspace is a subset of a vector space over a scalar field or a real field. Now, mathematically, we have a vector space with V, W as our subspace. Now, when we define what a subspace is, we say that W is a subspace of V if W itself is a vector space over what? Over K, that is over the scalar operation, that is with respect to the addition and multiplication operations given in questions. So that's when we can define what a subspace is. And there are rules guiding subspace, which we call properties. There are properties that guide us to know when W is a subspace of V. So let's look at that quickly. So we have properties of a subspace W. Now the very first property that we need to consider is that our subspace must not be empty. It must be non-empty. And at the same time, there exists a zero vector in our subspace. And this zero vector is a very special vector in the subspace because zero in itself is regarded as a vector. So any set that contains a zero in it is not empty. So let's proceed into the second one. Now this second one says our subspace W is closed under vector addition. That is, we can have that for every u, v that is in W, or u, w that is in W, any letters we can use. We also regard it as u plus w is also in W, or u plus v is also in W. Big W this time around. The big W represents our subspace. Now an example now is the three-dimensional Euclidean space R3. In such a way that when you add two three-dimensional Euclidean space, to give rise to a three-dimensional Euclidean space, and also for the two-dimensional Euclidean space, you also give rise to a two-dimensional Euclidean space. So let's proceed. So the third one now, it will be closed under scalar multiplication. So this time around, since we are talking about scalar now, you should need to put in mind that scalar multiplication, now the layman understanding of scalar multiplication is that it's only magnitude, it does not have direction. That is, it multiplies linearly, it operates linearly. Scalars are linear. They are not gotten from plotting a graph. The point that it is not a Cartesian product, it is not a Cartesian point like x, y. It cannot be represented like that. It is only vectors you can represent as a point on a graph, x, y. But as long as it is scalar, you cannot. So scalar is one-dimensional. It's just like a straight line. That's like a linear multiplication. So depending on the rules given in the question, take for example, when we are proving vector spaces, they can give you that k open brackets x1, x2 is equals to kx1, kx2. And at the same time, they can also give you a rule like k open bracket x, y in bracket is equals to kx1, ky1. And you could also change the question in such a way that it only multiplies x. So depending on the rules given, that's what you are going to use for solving or proving the vector space. But this time around we are doing subspace. So subspace can be defined based on our scalar and vector equations, like I said earlier. So let's look at what we can do. Examples. We'll look at some examples, 1 or 2 examples, and then from there we continue. So let's see our very first example here. So this example says we should show that W is a subspace of 3-dimensional Euclidean space, that's R3, over a real field R if our W, our subspace, is such that we have x, y, 0, such that x, y is also found in our real field, which could also be real numbers. So now we need to consider that in a 3-dimensional Euclidean space we have x, y, z. So in the question we will notice that our z, the position z now is 0, and 0, from what we have learned, is a special vector in our subspace. So 0 is considered also a vector. So this proves that our subspace is not empty. This is our first property. And also there is a 0. There is a special vector 0 that is always in our subspace, whether given in the question or not, because 0 is also in our real field, that is a set of real numbers. So let's look at our second one. Now this time around we'll be looking at to see whether it is closed under vector addition. Meanwhile, we have been given our 0 vector to be 0, 0, 0 in our field. So expressed in 3-dimensional Euclidean space, it is 0, 0, 0. If it is 2-dimensional Euclidean space, to be 0, 0. That is all. So let's move to if it is closed under vector addition. So this time around we consider our u to be x1, y1, 0, which is in subspace, and v is equals to x2, 2, y2, 0, which is also in a subspace w. So when we add these two, for it to be closed under vector addition, it must give rise to a new vector which is also in a subspace and is also in a 3-dimensional Euclidean space, which is what we have here: x1 plus x2, y1 plus y2, 0 plus 0. So this is in a 3-dimensional Euclidean space, so we can say that it is closed under vector addition. So for the third one now, to see if it is closed under scalar multiplication, we need to make use of a distributive property from our vector space, that is AU plus BU is in our subspace for every A, B that is in our key, that is in our scalar field. So we just take U to be x1, y1, 0. So from there, when we multiply by A, it becomes ax1, ay1, 0 in bracket. Then BU is also bx1, by1, 0. So adding these two together, they must also give you a 3-dimensional Euclidean space. So as we can see now, we have ax1 plus bx1, ay1 plus by1, 0. So we can see it is also 3-dimensional. So it is closed in a scalar multiplication also. So we can just conclude that okay, our subspace, our W is a subspace of our 3-dimensional Euclidean space that is over our real field. So let's take a look at another example that we have here. So another example here is we should show that W, which is x, y, z, such that x squared plus y squared plus z squared must be less than or equal to 1, is not a subspace of our 3-dimensional Euclidean space over the real field. And we need to consider that u, v is in W. So since a rule has been given, the addition of the squares of x, y, and z coordinates must be less than or equal to 1. So that means we can consider 3 aspects. We can either consider that we are having a x to be 1, y to be 0, z to be 0, or x to be 0, y to be 1, z to be 0, or x to be 0, y to be 0, z to be 1. So this is the only situation where we can square it and then we'll still have a number less than or equals to 1. So we'll just say, okay, let our u be 1, 0, 0, and w is 0, 1, 0. So we should check for our first one. So our first one, of course, is obvious already that it is non-empty because 0 is a vector, so it is non-empty, and there is a 0 vector also. Even whether it is given in the question or not, there is always a special vector 0. So the second one now is to see if it is close to under vector addition, which is u comma w in w. So when we add this u and our v, we notice that we have 1, 1, 0. Here, when you square this 2, it becomes 2 is greater than 1. So since 2 is greater than 1, it does not hold. That means it's not a subspace, because 1 square plus 1 square is greater than what? Greater than 1. So we can just see that it is not a subs. So you see, it does not obey the rule given there, because it is actually greater than 1. It is not less than or equals to 1. So the next one we will look at is our linear combination, that is linear space. Linear space, a situation where we will now apply some mathematical aspects of solving questions like like substitution method, elimination method, how to simultaneous linear equations. That is why it is called linear combination of vectors. So goodbye for now. The next episode is coming right after this.